Thanks for being here at my virtual presentation. My name is Sevickson Kwidama, and today I'm going to talk about how I use graphing techniques to untangle the osquery tables. I'm a lead security engineer at Dictu in the Netherlands, and I'm originally from Curacao, an island right above Venezuela. I first found out about osquery around 2018 when I was casually surfing the web and was intrigued by the refreshing take on endpoint monitoring. Since then, I've deployed osquery on approximately 6,000 systems, ranging from Linux, Windows, and Docker-like systems. osquery table combinations are almost endless. When I started looking at osquery, the version I first started using was 3.2.4, and this version had 199 tables, and that was already a daunting task to try to understand what all the data possibilities are. Version 4.6.0, the current version, has no less than 265 tables in total, counting on all OSs. There's a great amount of information that you can retrieve from different osquery tables. So in order to find related context for my threat hunts, I had to manually search through the table structures, sometimes even the source code, and with trial and error find the data I needed. Naming convention also is not always the same. An example of a use case that I was during a security incident regarding suspicious Chrome extension, where I wanted to get the extension script, and as the warning illustrates here, it is telling me to join it against the users table. But when I joined it, nothing was returned. I will explain in my demo. This and the manual test made me wonder, how can I visualize the relationship between osquery tables for data enrichment? Visualization of the connection between tables can help to understand the possibilities and how the tables can be extended. If you have a clear view of the connections between tables, this would make it possible to create one query to get the needed data out instead of running separate queries and joining afterward, and with less trial and error. Also, it can be very useful for creating subqueries. To get to the graphs, I had a journey of discovery. It all started a while ago when I stumbled upon the Threat Hunters Playbook repository created by the Rodriguez brothers. There, they talked about the Jupyter Notebooks. At first, I did not understand it at all. I needed some time to digest all this new knowledge. Around the same time, I also learned about osquery and wanted to use Jupyter Notebooks as an exercise to answer some questions I had around osquery. This resulted in my first public virtual presentation at InfoSec JupyterCon and also first blog post. Side note, I am not a developer at all, so most of my time went into translating my thoughts into Python with quite some help from Google. This resulted in graph version 1.0. The graph gives you a visual representation of the relationships. I use it to visualize the relationship between osquery table and columns. The graph lets you find out how you could use different tables to enrich data, and you could find unexpected relationships. Of course, you can join based on other column names and make complex queries, but finding the other columns can also be time-consuming. But only basing it on column names did not give me all I wanted, so the journey continued. I wanted to have a more reliable way to see the connections. Using the data gathered from running osquery gave me better connections, but also megabytes of data. So I had to use my acquired knowledge of Python and Jupyter Notebooks to filter it down and gather interesting data. How I use Python and Jupyter Notebooks to create the connections can be read in my repository and upcoming blog. The dataset I used was small, but gave a surprising complete view of the connections. Data input was just three Windows systems, Windows 10 and Windows 2012, running 4.5.1 and 4.6.0 versions of osquery. And for Windows, the total amount of tables was 95, and I could get information from 73 of those tables. Not all tables can give results, as some are evented tables or have specific constraints I could not satisfy. For Linux, I had a combination of Ubuntu and Debian, and macOS was running the latest versions. To get out of the tables, I had to categorize the tables to make the table selection logic work in my code. General tables are just tables that you can just run select star from like processes or route. External lookup tables is for the curl tables. Path constraints are tables that need the directory of file path to give results, like hash and ELF dynamic. UID constraint tables are tables that usually need to be joined to the users table. Specific constraint is for tables like registry and OGS that need very specific where clauses. And the unsatisfied are the tables where I could not satisfy the constraint, like evented tables and tables that need specific piece of hardware or software. After categorizing the tables, I had to categorize the data also to make it easier to filter based on some criteria. So for this, I made 5 category buckets, from less reliable to most reliable. Less than 3 characters, I filter out immediately, because it's not even worth the time to take into account. Numbers like PID and port are important fields, but often mixed because both have 4 to 5 numbers. Text fields like username and file name are more reliable, but depends on the table context. Temporal fields like time can give a very accurate combination of results because the numbers are very specific, but also here it depends on the table context. Long fields are in this case the most reliable, and with special characters can make it even more. Generating the data and creating the graphs was an interesting process that I want to touch a little on. I first created a portable Python script to get the data out. In this script, I used the table logic explained in the price sheet to get the most possible data out. After I had all the data, I used different filtering methods to filter out empty entries and duplicates and fields with not enough data. An important step was also to find a way to anonymize the data, but keeping the grouping associations for the connections. After this initial process, there was the merging, where I merged the data from different systems, which was also very interesting, on how you can merge data but keep the groups without losing the connections. For that, I used a specialized column. I called it an anonymized column that I then created hashes from, and also an intersect column that just gives all the table column combinations that are part of that group. Filtering was also important in this process. I also have granular filtering here for continuous improvement. When some connections are found that are not correct, I am able to get them here and generate a new graph. Now we are ready for the data analysis and graphing process. This process has 2 Jupyter Notebooks, one for preparation for sending the data to the graphing platform, and the other for data analysis of the acquired data from osquery. Since the presentation at JupyterCon, I have been in contact with another presenter from that conference, Graphistry founder Leo Mayerovich, and we have been working together to visualize the osquery graphs as good as possible. Each graph I create is for a specific OS. Graphistry is a great visualization and graph analytics platform where you can create very large graphs to use in, for example, investigations. But before we go to the graphs, I wanted to point out some interesting data gathered from the data analysis perspective that I will use in the graph demonstration later. Most field tables are the tables that osquery spits out the most information from. The columns in this part represent the table name and the relative percentage calculated against the total, and the percent of data actually used in the graphs. Windows Event Log and ASL are very interesting tables. I did not even know of ASL before I started my analysis. Most connected tables are the tables that have the most connections. The columns here represent the table name and relative percent against total connected and the percent of data from this table that is connected. Auto-exec is a table that is an aggregate of different other tables. So it is good to see that as expected, it would be the most connected, as the same data is also available in other tables. Processes are overall the most connected tables as expected also. So joins starting from processes might give some interesting extra insight. I will be focusing on Windows event log table and the use case given at the start in this demo. This demo will be focusing on the Windows graph and the Chrome extension content scripts table use case I talked about at the beginning. I already opened the GitHub issue for this specific use case. Also, I will show how you can easily group tables, columns together that have same data but different column names. In this demo, I want to show how I use the osquery data and the power of the Graphistry platform to visualize the osquery table connections. This is a complete picture of the connected tables on Windows. To get a structured view, I arrange the tables and columns as intertwined circles. The outer circle with the red nodes are the tables, and the blue nodes in the inner circle are the columns. Here you can see that the auto-exec is the most connected as expected, and name and path are the columns with the most connections. And services is the second most connected table. Graphistry also has some great filtering options. Using this filter shows all the nodes and edges that are part of the Windows event log table. Here you can see this table only has the PID column that has any meaningful connection to other tables. When I want to deep dive in the data, I change some settings so that it reclusters differently, showing the interesting connections more clearly. Here you can recluster and see which table columns to which tables are connected. But as shown in the data analysis, the Windows event log should have more connections as it is a table that returns the most data. How we can make this table more joinable, I will touch on in the next slide. The use case that I was talking about in the previous slide can easily be shown with the following filter. According to the warning, it should be joined to the users table. If you look at the schema for both tables, you see indeed that they have a column in common and the UID column. But when you recluster, you see there is no connection between any of the users table to this table. And this is correct because when you check the output from the table, the UID column is empty. I also have a filter to show the columns that are directly connected to each other, but have different names. This can highlight columns that might have a naming inconsistency. As I said before, the PID and the port columns are clustered as they have the same range of numbers, but with more granular filtering, this labeling can be avoided. When we zoom into the other cluster, we see that the nodes are highly connected and the names are SID and UUID, even store ID, showing a possible naming inconsistency on Windows. I'm also in the process of creating a dashboard to make the filtering and looking for connections much easier. This was just a small demo of the possibilities of the visibility that these graphs give. Talking about the Windows event log table, I think this is a table with great potential in making osquery a historical event viewer, like I call it. osquery is great in making snapshots of current state of the system, but less historical. This table will also greatly improve the use of output of sysmon in osquery and make the possibilities in creating more smarter queries against the event log. macOS also has the ASL table that has about the same kind of information. But on Linux there is no table like this. It is maybe an idea to create a table to read out information from syslog and the messages log. I already opened 2 feature requests to possibly make the Windows event log table better, and I am already talking with the main developer. I will talk more about these improvements in the next 2 slides. They are divided in parsing and query. The output from the Windows event log table is already looking good, but the data part with the most interesting information is not parsed, while it is outputted already in JSON. With a few small escape character changes, this will make it possible to be correctly parsed, and possibly shown in dynamic columns based on return data. Better parsing will make it possible to join more easily in columns, like username or SID. You can, for example, then get all events connected with a specific user or host name or IP to get a timeline. Another idea is based on a data analysis is to make searching more possible, more uniform with the searching in other tables. At this moment, by default, you have a small set of columns that you can search on. Using the XPath, you have more possibilities, but it is quite difficult to write. I had difficulty trying to transform this in a good XML search. The JSON extension is great and flexible, and also a good way to use for data fields, but quite lengthy, as you can see. I hope we can get to a point that you can write a query like the last one. This will make it much more easy to write and use for filtering. Based on my research, I had a few ideas that I want to share also. If we can incorporate the data from the table-column combinations in, for example, osquery itself or the website, we can give users suggestions on which tables they can best use for data enrichment. This will also give less trial and error, as you can check the graph for enrichment possibilities. The graphs and data can also be used to find naming inconsistencies and missing links from highly connected nodes. Creating a table to read out syslog and messages log for Linux might give Linux more historical power. JSON parsing for the data column and extra columns from Windows event log, and also the ASL tables. Another idea I have is to create output columns based on query output for tables like event log, where the output can be dynamic depending on event ID. Table labeling context, or you can call it contextualizing, can give a new user, even a seasoned one, easy overview which tables can be best used for what task. Need will probably grow larger as the table amount grows. Some tasks that I want to work on in the near future are creating joint probability calculations based on the column name and the data for, let's say, version 3.0. This will make it more flexible and accurate. Maybe use a machine learning or automated process to looking for relationships based on probability. Also improve the graph by adding more data and granular filtering, where the numbers get mixed up easily like in PID and port. Also add data from tables like evented tables or with specific constraints. The graphs are great for beginners, but also osquery developers. Developers can, for example, use it to fingerprint releases and debugging. Senior users can also use it in, for example, incident response or threat hunting. You can run a query and get information that need further investigation. If you can easily find out which tables you can use to pivot to, based on the results of the first query, you can enrich your results faster without having to look at all the tables and with trial and error. These graphs will also be featured on the osquery homepage, and I will also release a blog on the more technical details. Let's make these graphs better together, and also all the data I use to create the graphs can be found in my GitHub repository. Thanks for your attention while listening to my presentation. Maybe you have an idea or some expertise you want to share to make the graphs better. You can always contact me on Slack or other social media. And for questions, I will be available in the chat. Thank you.